Swayam Prabha. Digital India. Educated India.
So, we begin with a revision session today, and also some points which were raised. I will try to go through them. So, one of the things which was raised at some point was by some people is to how an auxochrome works and why does anything change. So, one thing you must understand is that whenever radiation falls on any material, depending upon the energy of the radiation. So, gamma rays have more energy compared to the visible range, and so based on that energy there is going to be some electronic transition. So, electrons will move from one energy level, which is a stable energy level, to an excited state. Let us say you have double bonded structure, the pi bonds are relatively more susceptible to this change. That means, they will absorb energy, electrons will go to a higher state, and what will be absorbed? Absorption will be at a certain frequency. So, energy is related to frequency and the wavelength in one way or the other, and so the shift takes place. And if you do any change in molecular configuration, then this shift could be enhanced, eased out. If it is eased out, then less energy or higher wavelength radiation can also do the same job. So, there can be some compound which look very similar, which may not be giving any color, but if you add something to them, they will start giving you color. So, one important thing is that there is a transition which takes place, all right, from one level to the another level, and then obviously it is a transition, therefore, it is not going to stay there only, electrons will come back and whatever they can do, they do. Sometime this can happen that some groups have responded to near ultraviolet range, but when the electrons come back because of various reasons, energy loss here and there, the final radiation which comes out is in the visible range. One of the thing which you probably understand is the optical whitening agents. They are colorless, but they absorb in the ultraviolet region, but while the electron comes back to a stable state, the energy released is in the visible range, and therefore, the brightness and so on and so forth that you see. So, one interesting thing is that unsaturation helps, okay. And so most of these so called chromophores would have unsaturation. So, there is a transition which will be made easy. So, what you are looking at is electronic excitation transition changing from a lower energy to a higher energy level, and of course, that is an absorption of energy. If the energy is very high, that this could actually go to such a state that you never come back to the same state, you can actually have bond breaking. But if the absorption or energy is in the range where it is able to come back to the state, then you have compounds which will be in the dyes and pigment range. So, one important thing is, other than an unsaturation, in the molecules there should be conjugation. Conjugation means alternate double and single bond availability in the molecule. If this is very nicely done, easily available, transitions become easy. It also is important, the molecule also exhibits resonance. That is, it has got one resonating structure versus the other resonating structure, both. If the resonance is possible, that also means energy absorption of some type going one state to another state, but they are stable states. So, this also helps in making the dye or the pigment a stable chromophore. You may be aware, like aniline black. Have you heard of this color? So, what happens is the aniline keeps on polymerizing, molecules keep getting added, and you have conjugation being increased. As this conjugation keeps on increasing, it becomes a different color, from a pale blue to a green to a blue to black. Right? This is how the colors change. So, conjugation, if it is more, you are going towards a deeper depth of shade. Auxochromes are such groups which do not by themselves give any color, that is, they do not absorb in the visible range. They do absorb, they will absorb infrared. So, they will absorb, but it is not visible to you. But if you have infrared spectroscopy, you will see every functional group absorb something or the other. But what we are interested in, what can be visible to the eyes, and that is what becomes color. It is, as far as the absorption is concerned, every molecule will go through this process of excitation of electron and vibrations, etc., which also means you have absorbed some energy. That is why you have started vibration, but only at a particular frequency. That is the important part. So, there is this compound which you can see is azo group has, but it is a methane, dimethyl group is there. On the other hand, you have azobenzene type of a structure, and so in one case, in both the cases you have azo group, but enough conjugation is not there, and so you see it absorbs radiation, but also in a region which is not in a visible range. So, just having an azo group does not mean that it is going to give you color, it has to be supported. And one of the interesting thing of support is this conjugation. If you see this, so you have this group, double bond, single bond, then you go there, then you have a double bond, then single bond, double bond, single bond, double bond, single bond, and things like that. One can always, if you can provide some of this type of structure, then suddenly you will feel, you will get some color. If by any action your conjugation is somehow stopped or restricted or diminished or reduced, then also you may not be able to get color. For example, the phenolphthalein, which you must have used as an indicator, in an acidic medium, is colorless. In alkaline medium, it is pink. So, if you see here, there is a double bond and a single bond, then double bond, double bond, double bond, then double, and from here it goes there. So, there is a possibility here, double bond, double bond. Here it starts breaking, it is all single and there is no conjugation very easily available, and in this range there is no conjugation available, and so this becomes a problem. So, if it is a continuous conjugation, it will help. I mean, even if it is CH2, CH2 or CHR, okay. So, this type of a single bond conjugations, if you can create, then also you will be getting even a linear molecule or an aromatic molecule, does not matter. The other thing which we said is the resonance. So, you see there is this methylene blue, you have a good from here onwards conjugation, there is a conjugation, and there is a positive charge on sulfur. This compound is stable because it resonates. Another structure is where this positive charge is on nitrogen. So, it has shifted. This chloride ion can be anywhere. So, if you have this type of structure which also resonates and also remains somehow conjugated, here there was a conjugation because of sulfur, here you have through this any link that you can make, and so the color remains stable, it does not change. If you have resonating structure, so there is a conjugation, approximately the number of groups that are available are similar, the number of conjugations remain same, and the chromophores, whichever, for example, dimethyl nitrogen or 2 methyl groups here, they remain the same, and so the color does not change, but it becomes a much more stable structure. A malachite green, for example, can have this nitrogen, the plus charge here, which can in another resonating structure can go there also. And so, if it is possible to have conjugation, if it is possible to have resonance, then you will have a more stable structure which will give color, all right. So, it is a simple triphenyl methane structure. So, there is a shift which we call as a bathochromic shift. By adding some groups, you can change the wavelength towards higher, longer wavelength, which is towards the red part of the spectrum, and therefore, sometimes also called the red shift. So, either you add a substitution which we are calling as an oxychrome, or sometimes when something dissolves, it also has some effect. So, bathochromic shift. How can it happen? It can happen if you have electron donating groups, the same azobenzene which you had seen, if you add something like NH2 or OH, things will be different. If you also have a possibility in a molecule that there is an electron donating group like an NH2, an electron accepting group like NO2, again placed in a manner that they have become part of some conjugation. So, like one is trying to take, the other is ready to give. If this happens in a conjugated area, then also it helps. Or the electron donating group like this NH2, instead of H, if you add alkyl groups, instead of NH2 you have 2 methyl groups, for example, on the nitrogen, then also this will start changing. So, OH versus this, we can see NH2 and NO2 placed in a manner that they help each other, and the electron donating effect of NH2 can be increased, or any other amino group could be increased by adding alkyl groups. Look at this structure. You have OH here, there is a lambda max, some 347 nanometers. If this is changed to NH2, it increases because this is more electron donating. If you have here, as in a thing at the end of a conjugated structure, you have NO2 and goes further. So, same structure, same chromophore, more or less chromogen also is same, except now the oxochromes are being changed or added. All right. So, there is a minor shift. A red may appear a different red and a blue may appear a different blue. Those kind of things can happen, and that is what an organic chemist is going to be working on, making a new molecule, adding something. Some of these principles will be used. For example, the same thing, instead of NH2, you have a group like alkyl CH2CH3 or CH2CH2OH also added, and the wavelength of this wavelength means lambda max. You understand the Bayer-Lambert's law, you know that, right. So, we are worrying at the moment about the lambda max, because if you take a visible spectrum of any colored compound, you will get absorption maxima. So, wherever a solution is possible, we go for the absorption spectrum. If you have a textile material, fabric, dyed, printed, then you will have to go for reflectance. And so, there is a relationship between absorption and reflection or reflectance, and that way you will be able to understand how much dye is there or how much shift is there. These things become important sometimes. These small changes can also happen in a solution also, or on the fiber, if there is a possibility of aggregation also. So, sometimes even when you do some aggregation, there also there can be some shift. It would appear as if there is a change in color happening, but that also can be seen either by a change in the lambda max or appearance of a doublet. So, the wavelength or the waves, the spectrum may be having more than one peak. If you have a mixture of dyes, then also the spectrum can tell you that there are more than one peak lambda max, and therefore, this can, because the absorption spectra are additive in nature. So, if I have one molecule of a dye and the other molecule of other dye molecule, and if you mix these products, then based on their concentrations, you will get the absorption peak and the height, the intensity, that is based on the concentration, but the wavelength is based on some of these things. So, if there are two of them in equal moles, then you will get two peaks characteristic of them added together. People have written some questions on pigment printing. So, I am just trying to make sure that we all think in the same lines. So, pigment printing wanted a zero solid thickener, because you are making a film of a binder, and if it can bind a pigment, it can bind any other particle also. And so, if there is a 0 solid, that means during curing itself everything evaporates, nothing is left behind. Then the film is more transparent and the print would appear brighter. Okay. Oil emulsions are therefore were always suggested for this reason, and they still give the best results. There is no doubt about that. If at all one has a problem, is because of the environment and fire. These are the reasons why people would not like to use oil, or they would like to replace the oil emulsion. And therefore, there are many synthetic thickeners who are not, which are not polyelectrolytes. Okay. So, every thickener is not a polyelectrolyte. So, you can have, so their viscosities would depend on what is the concentration of that particular compound in any solution that you make. So, the concentration dependence of and the molecular weight dependence of the viscosity is done. The more is the higher is the molecular weight, higher with viscosity, nobody will doubt about that. Higher is the concentration, higher will viscosity, there is no doubt about it. But the polyelectrolytes give an additional advantage, that at a given pH, you could have acidic groups or amino groups, whichever you can put in a polyelectrolyte. So, the acrylic acid based polyelectrolytes, when they get negative charge, let us say, they start repelling each other. So, even if the concentration is low, the molecular repulsion itself is so high, because you are still contained in some environment which has some dimensions, and therefore, the viscosity increases. This is the third dimension of viscosity increase. One is concentration, other is molecular weight, and if you have a possibility of creating repulsion between the molecules by generating same charges and in large numbers, then also viscosity increases. So, this is the reason why for pigment printing some such type of thickeners also have been suggested, because at a relatively lower concentration they can give printable viscosities, which could be in the range of 15,000, 18,000 CPs. So, if you can get this in 0.5 concentration compared to, let us say, a normal starch going to 6%, 7%, or alginate in 3%, 4%, 5% based on molecular weight, then you say, well, it is not 0 solid, but it is a very low solid, and therefore, it is not going to give you, it will give you relatively brighter prints, pigment prints, and will not have the problem of environment, fire and other issues. So, reactive dyes, which are the most popular dyes for printing also, they are obviously water soluble, as you are quite aware that they were initially synthesized for cellulosic, cotton and others. This question of reactivity and substantivity came only because they would hydrolyze. When? At the same condition where the reaction takes place with cellulosics. So, reaction takes place in alkaline medium. Water also has got enough hydroxyl groups, and so in alkaline medium dye would have the tendency to hydrolyze first rather than at a later stage, because the accessibility of hydroxyl groups in water molecules is much easier compared to even a large polymeric molecule like cellulose. You still have to go at some place only. The hydroxyl groups are not free. In water, they are just moving, everything is mobile. So, from the probability point of view, hydrolysis or hydrolyzed dye is a more expected outcome. So, while if covalent bond has happened, has been made with the cellulose, after that it is difficult, relatively more difficult for the dye to come out of the substrate. But if before that reaction has taken place, hydrolysis has taken place, then the hydrolyzed dye is just sitting there unreacted, just like a direct dye. But obviously, its structure is not as large as a direct dye, and so every wash it will like to come. And so, the wash fastness of reactive dyes has not been 5, which should have been just 5. There is no question of it being less than 5, but it is almost never 5, and that is because the hydrolyzed dye always happen. And therefore, in dyeing they improved the processes that first you exhaust, so that most of the dye is somewhere near the fiber and molecule and hydroxyl groups of the molecule of cellulose rather than in water. So, first you exhaust and then add alkali. All right. In printing also people can do all kinds of things. We can always make alkalis which are latent, only at the time of fixation they will become active, or add a mild alkali, or use dyes which are not so reactive. All right. That is the reactivity issue. So, you are not really looking at very high reactivity of a dye. Substantivity, normally everyone would want there should be high substantivity of a dye molecule, so that it goes to the fiber. Here the high substantivity also meant that the hydrolyzed dye, if it is more substantive, would not get washed off easily during your washing processes. You have printed, drying, fixation, washing, and keep coming out at different points of time. And therefore, they wanted the substantivity not to be too high, because if it has reacted, then substantivity has no problem, no meaning at all. It is only if it is not reacted, then there is a problem, because you are, let us say, trying to create conditions where reactivity will be moderated in a way, and conditions will be created so that cellulose reacts more. So, less hydrolyzed dye having lesser substantivity would also mean that it will be washed off easily. So, in the customer side you will have more satisfaction if there is a hydrolyzed dye. The interesting thing that obviously happened at a later stage was that it was found that they are all good for protein, and polyamides, so protein based fibers, polyamides. The reaction with these groups of the amino group, end amino groups, can take place in acidic or neutral medium, covalent bonding also. If this is true, then obviously there is no hydrolyzed dye or the chance of any kind of hydrolysis of a dye is minimized, because it requires alkaline medium to hydrolyze. So, in these cases you found that this the same kind of a dye has become much more acceptable, because it would not hydrolyze, because your pH conditions are different, and that was the maximum highlight. The highlight of these reactive dyes now is that in the protein and polyamides type of material, you can dye with them, print with them, and you would have least chances of production of hydrolyzed dye. So, that is one point. So, this is somewhere it comes, you can always. Some people also always have some kind of an issue with direct and acid dyes. I saw some questions and some answers, quite simple answers like direct dye can have more than one azo group, acid dye will have only one azo group. That is not true. One of the important thing is that acid dyes are basically organic acids, then they are generally smaller molecules. Both of them are anionic because they have water solubilizing group, but direct dyes are large molecules, approximately linear also, so that their substantivity towards cellulose is higher, although they do not make ionic bond, they do not make covalent bond, they make only hydrogen bond, but the lengths are such that they almost go and fit. So, affinity, substantivity of a direct dye towards cellulose is high. It does not mean that you cannot dye wool with direct dyes, because they are also ionic. Only thing is a large molecule, ionic. Acid dyes are smaller molecules. That is one thing. But acid dyes, if you dye in the same pH environment, the wash fastness will be low, because they are not substantive, right. Azo and azoics, I am just repeating this here because some of the answers that I read were not very clear. The manufacture of azo dyes is also done exactly in the same manner as azoics are produced. All right. The only thing is that is being done in an industry, the chemical industry. They also have to, if you make an azo group, the only way to make an azo group is diazotization and coupling, diazotization and coupling. There is nothing else. The azoics means that the diazotization and coupling is being done in situ on the fabric. That is all. And other thing is, as far as the production is concerned, you are producing in the same manner in different places, that is all. The only difference here also is that you are, in this case you do not have a solubilizing group. Where here, based on a dye, you may have a solubilizing group. If you do not have, then it is going to become like a pigment or a dispersed dye. Dispersed dye also may have some ionic groups, I mean the OH or some such groups which would make solubility less, but not 0. So, that is one difference, and therefore, wash fastness of azoics, because they are synthesized in situ is high and they do not have solubilizing group. But in case you have more particles being generated, which of course will be there, then you can have rubbing fastness, wet rubbing particularly could become poorer. There was one question also, people trying to answer this in one way or the other, related to basic dyes. Basic dyes in, obviously now you know, and most of you, whosoever has answered this correctly, that they have positive charge and that positive charge is generated in acidic medium. All right. In alkaline medium there is no positive charge. So, you can't dye or print in alkaline medium. Dye will not get destroyed, but the mechanism is not available for that attraction fixation. Like in cotton, cotton has no affinity for such dyes, but they can be attached through a mordant. All right. Basic dyes can be dyed onto cotton via a mordant. So, what we had talked about is the light fastness of the same dye when it is linked to the cotton through a mordant which makes hydrogen bonds and so on and so forth, and so some fastness increases, is not dependent on the ionic nature, versus acrylics which have negative charges and a positive charge automatically has affinity in that electronic way and goes there and gets fixed. In the first case, the same dye shows lesser light fastness compared to an acrylic. One of the reason was the cotton is hydrophilic. So, there is enough moisture available. So, based on the temperature, you have chances of peroxy radicals being formed with radiations, and if it is, that also leads to a reduction in the fastness property. Also, the energy transfer, the absorption energy, like we said that whenever something is interacting with an electromagnetic wave, there is going to be an absorption at a certain frequency and therefore, you see the color. If it absorbs more for whatever reason, because when you actually talk about light fastness, your electromagnetic radiations are obviously not limited to visible region. They are ultraviolet, strong ultraviolet, which obviously can break. Now, this energy, and when the electron get excited, goes there and becomes so high, then you can actually break the bonds. So, instead of that, if the immediate absorption of energy can also have a mechanism of transferring this absorption through a link, in this case an ionic link, to a fiber, then you can damage the fiber, hopefully not so much, but the dye itself can be saved. So, if there is a channel of transfer of energy absorbed to the fiber efficient way, then fiber being a larger molecule and things like that, it can absorb also, maybe some changes can occur in terms of some vibrations happening, maybe somewhere a bond may break as well, but you will be seeing that light fastness is high and it is more hydrophobic. So, less water available at any given point of time, and so that peroxy radical formation probability reduces. You can't say never, nothing will happen, because we have oxygen all around, radiation coming, any polymer molecule will also degrade. But relative basis, if you can have channel like this, then the same dye shows you better results in terms of fastness. There are some questions and answers written on this topic as well. So, dispersed dye on polyester. Dispersed dye is also more hydrophobic, polyester is also more hydrophobic, and therefore, this is the suitable dye for this fiber for printing as well as dyeing. So, there was a question which was answered. So, as far as absorption part is concerned, so you have solid state dyeing isotherm. So, wherever there is space it goes. Affinity of course is because both are hydrophobic, and of course, whenever there is a possibility of such type of molecules coming together, they will like to come together in preference to water, because they are not water soluble and they are dispersed, and therefore, it is clear that they do not like water. So, whenever there is a chance, they will like to go to that particular material which is other than water, which is hydrophobic. And that is one reason that aqueous dyeing of polyester or even printing of polyester through aqueous based paste is a preferred process, because theoretically dye does not like this, it wants to go somewhere else. Okay. So, that is the advantage you get. If you take an organic solvent, then means the dissolution takes place. I mean, the whole game of getting a hydrophilic dye on a hydrophilic fiber is being played between the water, which is a solvent. Dye likes the solvent also, and the dye likes the fiber also. Therefore, you say let us increase affinity, do something, so it goes more toward the fiber. In this case, it is almost built in, it just likes fiber. But if you make it organic solvent, then this equilibrium will shift towards the solvent, all right, and therefore, aqueous medium is good for the disperse. The pH is also approximately acidic, not in the alkaline. Some people have talked about this, saying that this tinctorial value is K by S, which is not a good way to express this. So, this is based on the reflectance values, you get a value which is proportional to the dye on a surface which is seen. Dye which is inside, obviously it does not see, but this value can change based on the substrate itself, and therefore, saying that well it may get related with the tinctorial value. A tinctorial value is the amount, the kind of a color perception that you get at a given, let us say, mole of a dye, right. K by S is measuring a perception based on how did I dye. So, this is, while it is okay that whatever I see is reflected through the K by S value, I am happy or sad, but if you do a bad job, let us say same amount of dye, if it is on the half of the fiber cross section on one side, will appear darker compared to the one which is completely absorbed. So, therefore, it is not reflecting the property of a dye, right. The tinctorial value is a property of a dye and not dye fiber combination. So, just saying that it is basically K by S is not a right way of looking at it. Exactly same thing should be there. Let us say a white surface is there which actually just makes a monomolecular layer on that white surface, which is a standard white, and you know exactly how many moles are there, and then you compare 2 dyes, 3 dyes, 4 dyes, then you can talk about this value also. And this also is based on, to start with, we always measure this as lambda max. Well, it is not the area under the curve of a spectrum. If you do that kind of energy thing, that gives a different value, right. So, while it may be related, but it is not this, right. So, I think we can stop here for today. This is the kind of revision we thought we will do before we take the final exam. All right, thank you.